All right, so let's look at number 10. Because I think when I walked around, some of us had 10, but not a lot.
That was me. That was me, guys.
No, it wasn't just you that missed it, though. Like, I mean, some of you had 10, but some of you didn't. So, when we drew our picture, how many of us... Oops, sorry, I made it 3, but it's only 2. It's only 2.
Then it's all... Okay, I didn't like
I
that.
started to draw my other number 11 or whatever. Okay. Again, like I said, I try to label the widths always the horizontals and the lengths always the verticals. So typically when you see me label, I will make the tops and bottoms W's and the sides L. It makes it easier for you and I to be consistent. Because if I use W where you used L and you use L where I use W, then your math starts to become a little crazy. Did we all label our picture like that? How many of us did not label the middle line L?
I did like.
I counted that.
I did like W and W, so that it was like 2 separate.
Okay. How many of us got a perimeter of 3L plus 2W? Because we considered the fact that the middle line needed to be fencing. And your area is still what?
LW.
Yep, still LW. So, what we were given was the area, right? You were given that the area was 216. So what we could do is use that to come up with a relationship to turn the perimeter to a single variable. Yes?
I thought the first part only asked for the perimeter of the outside. That's what I thought when I read it. That's where
No.
But it asked for the length of the fencing.
Yeah, it asks for length of fencing, which
Yeah,
means
I
the
thought it asked
fencing,
for both. I know it did ask for length of fencing.
Oh.
but I thought
it asks for the dimensions, which is length and width.
Okay.
However, it said, what are the dimensions that will minimize the amount of fencing, but maximize the area? So that's where I think the wording was catching you. So we have to get an area of 216, and we want to use the minimal amount of fence. So we say, all right, let's say that W equals 216 divided by L. So now when I talk about perimeter, we're going to say that the perimeter is 3L plus 216 over L. So you get 3L plus 216 times 2 is 432 all over L. If we're trying to minimize or maximize the amount of fencing, we want the derivative. So we're going to find the derivative perimeter with respect to the length. So 3L becomes 3 minus 432 all over L squared. Create your common denominator. So you get 3L squared minus 432 all over L squared. Again, we don't want a length of 0, so we can kind of eliminate that denominator. We're going to set that numerator equal to 0. And solve for L squared. So 432 divided by 3 is 144. Square root of 144 is plus or minus 12. Again, can't have a negative length, so we kind of toss away the negative L. Therefore, we want to just check that a positive 12 is going to maximize that perimeter. So we want to make sure, minimize that perimeter. So I make sure it's a negative on the left and a positive on the right. So maybe I plug in 1. So if you plug in 1 to this derivative, you get 3 minus 432. Well, that's clearly going to be negative. If you plug in something like 100 squared is going to give you a really, really big number, minus of 432. So once again, we have the positive. So we can verify that this is in fact a minimum. So the length is 12. So you have 12, what was it, feet? Meters? 12 meters by, then you take your 12, plug it back in over here, and we get 216 divided by 12, which is 18. So the dimensions that will minimize perimeter, maximize area, is 12 by 18. The 12 is being used 3 times. Yes?
What if the 12 was the maximum, but they were still asking to find, like...
Then you did your math wrong.
Oh.
So, like, that's typically, like, if you're at, or unless you have, like, multiple values. So, like how in this case we threw out the negative. Sometimes you might have a positive 12, a positive 8, and a positive 4.
Okay.
So then you have, like, it might be 4, 8, and 12, and you have to find which one is the min.
Okay, got it.
So, but yeah, typically if you only get one number that's going to fit the domain, and it's the wrong thing, I would go backwards and check your math.
Okay, there's not like an extra procedure.
No, there's not, like, if you get, like, something that's pretty false, these problems are pretty cut and dry.
Okay.
There's usually an answer. They're not setting you up for a trick. It's not like there is no minimum value. Yeah. All right, let's take out yesterday's notes. We'll finish off what we didn't do yesterday. So I know we kind of jumped around a little bit because the slides were in a different order.
Are we on the cylinder?
Yeah, we may be going backwards too. So, did we finish the 192 one? I don't think we did.
Oh, you mean the poster?
Yeah.
No. I don't remember putting it in there. I started doing it back. Putting it in there.
That's nice. So we at least got to this point with the poster.
Yeah.
Correct?
Yes.
All right, and then we were even like a little bit further, right? Because we found the derivative.
Yeah.
So we got to the point where we said, okay, this was foiled, and then we derived it. So we got that dA dx was equal to 6 minus, and I never multiplied the 4 in the 192, but 4 times 192 is 800 minus, what? It's not, it's 800 minus 4 times 8, which is 32, so it's 768.
That's exactly what I told you.
You did it.
Does.
Nico.
Nice paper.
Thank you.
Okay. The poster problem.
Not like that.
Keep going back to front.
No.
You didn't even look.
There's no one.
Promise.
There's no people. We good? We're about here, right?
Let's see.
That's
We did Y. We did
D-A-Y.
It's
we plugged 192.
everywhere I have an X, you have an Y. It won't change it. It's literally the same thing.
Yeah, we
Oh, 670. My dinner.
Because
Which
we
one's-
solved for x instead of y. Like,
Weird.
Why did I have a plus B? Yeah.
that's what we did.
Yeah.
But I mean, the numbers should. Does it change the 6 then too?
I think so.
Yeah.
Yeah.
It would,
That's
6
plus
would be a
4.
4, then it'd be 6 times 192. Okay, we're late.
Okay. So we did that.
Yes.
And then I did this.
Where did I put it? You can please put it on. Nobody's
Yeah, I was just like reading.
Because yeah, it's 6 times 192 now instead of 4.
1,152.
What is it? 1,000 what?
152.
So we should do that. Ugh, I did it with X's. X's are smaller numbers. Okay. So once again, denominator we don't care about. We're not going to have a length of y. That wouldn't make sense. Or y equals 0 rather. So we kind of toss away the denominator. You set your numerator equal to 0. Solve for y squared. So when you do that, 1,152 is a perfect square, 4 is a perfect square. So I end up getting 34 over 2, which is 17. Okay, so if we get a 17, right? Quick around centimeters.
I don't think it's on the dot though.
It's got to have some sort of decimal. I just don't know what it is.
It's
That's it.
16.97.
There you go. So I rounded up to 17. Okay. Verify. So once again, plug in 1. So if you plug in 1, you can plug it into either step. But again, we're going to get a positive that's really small minus a really big negative, so you're going to get a negative. Plug in something bigger like 20. Well, 20 squared is 400. 400 times 4. It's going to be 1,600, which is bigger than the negative. Therefore, this is positive. Therefore, 16.97 is in fact a min. Plug 16.97 in over here for y, and you get x equals 11.3. So the dimensions of the poster on the inside are 11.3 and 16.97. That is the inside. It says find the dimensions of the poster with the smallest area. That is not the dimensions of the poster. That is not the dimensions of the poster. The dimensions of the poster are 11.3 plus 4. And 16.97 plus 6. So that's where AP catches kids. You give your X and Y answer and you kind of quit. But they didn't ask for the dimensions of the printed area. They asked for the dimensions of the poster, which includes the margins. Does that make sense? Like, kind of see where they were throwing you off a little bit. Okay. Let's talk about the cylindrical can. A cylindrical can is to be made to hold 1 liter of oil. Find the dimensions that will minimize the cost of the metal to manufacture the can. What do we know about a cylindrical can? If you had to draw it as a picture, think about a coffee cup. Think about a can in general. You have a cylinder with a top and a bottom. So if it's holding a liquid, it has a top and a bottom. Those tops and bottoms are circles. If I took my can and I opened this up and laid it flat, the sides of the can are actually a rectangle. So if you took the material to make a can and opened it flat, it would be a rectangle with 2 circles. This length here of the rectangle is equal to what?
So that's circumference of the circle.
The circumference of the circle. So the length here is the circumference of the circle. So when we're talking and we're trying to talk about surface areas and volumes, those are key things to help us understand. So area of a circle is what? Pi r squared. How many circles do I have?
2.
So if we're talking about surface area, it's 2 pi r squared. We shall call the height of the can h. So again, this is circle radius r. So we talked about these. The area of the square would be what?
Circumference h times
Yeah, so what is circumference?
2 pi r.
So surface area would be 2 pi r h. That's where like that formula that you were given in geometry all those years came from. I know. But now you do know. How about volume? What's volume of a cylinder?
Pi r squared.
Yes. So again, volume would be pi r squared times h. So it's the area of the top times the height. What were we given? We were given that a cylindrical can is to be made to hold 1 liter of oil. That 1 liter would represent what in terms of formulas we have? Volume. Is a liter considered a length in terms of volume? No. What would we want to turn that liter into? 1 liter is equal to what in terms of actual volume that would be helpful to us? It's in centimeters cubed, if that helps. Yep. Yep. 1 liter is 1,000 centimeters cubed. 1 liter is 1,000 centimeters cubed. That's something you want to make common knowledge. Plug your 1,000 now in for this. So you get 1,000 equals pi r squared h. Remember, we like to write things in terms of one variable. What variable is going to be easier to solve for in this problem? H. Because the other one has a square on it. And there's multiple r's here versus just a singular h here. So we're going to say, all right, h is 1,000 divided by pi r squared. And we're going to get rid of the h in my surface area. Because again, it says what will minimize the cost of metal. So we're trying to minimize the material to make the can. So we can now say that surface area is 2 pi r squared plus 2 pi r times 1,000 pi r squared. So what's nice about this? Goodbye to a pi. Goodbye to an r. So you get 2,000 r to the negative 1, or 2,000 over r. We'll finish this when I see you at the end of the day. Plus all the periods of the day in between.
Oh, now that was the intermission finale.
I was saying the show has started. All right, so we left off by talking about surface area and its formula. What we want to do now is derive surface area. So the derivative of 2 pi r squared derivative of 2,000 r to the negative 1 comes negative 2,000 over r squared, or r to the negative 2. So once again, we like to create that common denominator because we don't care about the zeros of the denominator. So it makes the zeros of the numerator easier. So that means we need an r squared over here, so we end up with r cubed. And then what we want to do is set the numerator equal to 0 and find the zeros of the cube root. So we get 0 equals 4 pi r cubed minus 2,000. 2,000 divided by 4 is going to give you 500. So we get 500 equals pi r cubed. 500 divided by pi is going to be first decimal again. So you get r equals the cube root of 500 over pi. Which I didn't write down its approximation.
This is so much easier to solve for this.
Something in the 5 zone.
I got like 4.
I was just guessing.
Oh, wait.
5.419. So I don't know how you got 12.
I should.
But my prediction of something in the 5 zone was pretty spot on.
Just got named. Cool.
You would be concerned that I couldn't actually figure that out. So again, cube root of 500 over pi is 5.419. So again, a radius of 5.419 seems pretty logical. You could verify again that it works. We always want to go back in and find the h value, so you'd have to take 1,000 divided by pi and take 5.419 and square it. Make sure that you always have 3 decimals. Make sure that if you're actually doing this math, you put the entire denominator in parentheses. And you get a height of approximately 10.839. Remember, they don't care if you truncate it fully. So these are in centimeters. So again, I know if you actually did it, you get 8395. So the 9 you could have rounded up, or you could have left it as the 9. So you could have made it 84 or 839. You can just directly chop it off or round up. Okay? Let's go backwards and talk about the other 2 examples that we did not do earlier. So let's talk about the one with the point on the parabolic curve. And what's the other one with the box maybe? Slope. So a distance problem. Okay, so it says find the point on the parabola where y equals x squared that is closest to the point 1, 4. So when you're thinking about this, we know that this is the parent function. It goes through 0, 0, it goes through 1, 1, and it goes through 2, 4. So there's our parabolic curve. And it says y equals x squared that is closest to the point 1, 4. So again, we're trying to talk about this point here. So we're looking to minimize a distance from this curve to this point. So we're using the curve and we're using the distance formula. So you're minimizing distance. So we're going to minimize the distance formula. So what that means is, I don't want to call it y. We'll call it the distance formula. Anybody remember the distance formula?
It's like the y squared of y1 plus y2 squared plus x1 plus x2 squared.
Super duper close. Instead of the pluses, though, you're going to subtract the distance between them and then add those 2 numbers. But yes, it is the square root of y2 minus y1 squared plus x2 minus x1 squared. So we could call our point x1, y1. And then if you're thinking about that, what are you going to do, or how are you going to come up with a way to talk about x and y for the x2 and the y2? What would those be representative of? I mean, we could leave them as the subscripts, but really they represent my answer, right? So if you want to keep the subscripts, you can leave them. If you want to just call them x and y, you can call them x and y. However, calling them x and y, what does that do to my problem? It gives me how many variables? 2. And it gives me variables not together. And I really don't want to do implicit differentiation right now. So what could I do to turn that distance formula into a single variable? What relationship would I have with x and y that I could use to get rid of a variable? What's a relationship I know with x and y? Yeah. I know that y is x squared. So if these just represent points x and y, to get rid of the y's, I can replace it with x squared. So that I can say the distance is the square root of x squared minus 4 plus x minus 1. And our goal again was to what? It was to find the point on the parabola closest to the point 1, 4. So my goal is to minimize distance. So I am trying to minimize distance. To minimize distance, what do I need? Yeah, I need the derivative of distance, right? So the derivative of the distance for a square root would be 1/2 x squared minus 4 squared plus x minus 1 squared, all raised to the negative 1/2 times the derivative of the inside. So derivative of this would be 2x squared minus 4 times 2x plus 2x minus 1 times 1. What do you notice about this problem and that problem? They both have a
2.
and I have a 1/2. So I could GCF out my 2, and I could multiply it by the half, and they're going to cancel. So that at least cleans it up a little bit. So now my derivative has a numerator, and I'm going to distribute while I multiply here. So 2x times x squared is 2x cubed. 2x times 4 is negative 8x. And the 2's go on here. 1 distributes in, so it doesn't change anything. But I get plus x minus 1. We good for the numerator? Denominator is just the square root of the original distance formula, right? Okay? So, do I really care about the derivative's denominator being a 0? No, because that's when the derivative does not exist. And that's not really going to give me a max or a min. That's going to give me an asymptote. So what I do care about is when the numerator is equal to 0. So my numerator is 2x cubed minus 7x minus 1. So I need to find the zeros of that numerator. So go ahead now, use your calculator because they're super gross, they're not pretty, and find me those 3 zeros. This is the case where I was saying you need to know maxes or mins and make your number line charts. Because we are going to get how many roots? 3. So go ahead, take a minute. Find your 3 roots, put them on a number line, and determine are they mins or maxes. cheating.
Indeed.
So again, once you find your three zeros, you have to compare the positive and negatives around them to determine if it is a min or a max. So once you found them, great, but then I want you to also put your positive and negative values on the number line. So I would say no, but it doesn't tell us that we're dealing with the first quadrant. It says find the point that is closest. So, I mean, yes, we know logically if this is, so I believe when we do it, right, it goes negative, positive, so that we have a min here and a min here. This point is almost like that symmetric zero. So like it would be over here. So we know logically that point doesn't make sense. But in terms of showing your work, I would still show it as a root. And then I would justify why with what you just said and we said. So that, you know, we have two minimum values. However, because 1.938 is significantly closer to 1.4, we use the point 1.938 as our minimum value. So the point 1.938, and again, you have to be careful. It says find the point. So I would say if it's asking you for a point, it's asking you for an ordered pair. So you need to take this 1.938 and you actually need to plug it back into y equals x squared. So I would say the point .938 comma that number squared is the closest point 2, 1, 4 on the curve y equals x squared. This is 3.755. So again, logically, if you squared this number, it would still be a positive number. And it would be close, but it would be, we're talking comparing this point to a point way over there. Clearly, that's the smaller distance. Okay? Your homework is going to be in the books again. The slope problem takes a good bit of time, and since we only have 6 minutes, I don't think we'll get through it, and it's not one you need to actually be able to do your homework. So let's talk about things to remember as you're looking at your homework. Remember, if the function that you want to optimize has more than one variable, use substitution to rewrite that function. If you're not sure that the extrema you found is a max or a min, check it. If the endpoints could be maximum or minimums, check that. So most of the problems we've looked at so far have been open-ended. However, if they give you a definitive domain, EVT stresses you must check your endpoints. So again, if you have an optimization problem and they give you a domain, check your endpoints. Oftentimes they're setting you up for an endpoint to be the value maybe you need. Okay, so we're looking at page 226, 11 to 19 odds, plus I want to add on 16.
You said to remind.
Yes.